Okay, good morning, everyone, or good night, good evening, wherever you are, and welcome back to our first ever new episode of Mathcal Math with Stories. In this episode, we're going to explore something that's fundamental to the entire concept of mathematics and something you have learned since you were three numbers. What we count with. Well, you may say, well, I count with fingers. Well, that too. You can count with fingers, but that's not the scope of our discussion, and get away from my episode, you idiot. Anyway, so as we first approach numbers, we may think of the concept of counting objects. For example, one counter, which is an object, means one. Two objects, which is two counters, means two. Four counters is four, so on and so forth. And this is how most of us has approached numbers early on in our lives in preschool. We know that numbers are meant to count objects, and this is a motivation behind the invention of the so-called positive integers, the counting numbers. And we can represent those integers, those numbers, as points along a line. If this point represents 1, then this one is 2, 3, 4, and so on. And those points are equally spaced, the distance between them are equal, and we can go all the way up. It is allowed. We can approach some really big numbers, some really big integers by going to the right. But of course you may ask, what happens if we go to the left? Well, you're not the only one with that question. Our ancestors have always thought about how to go everything differently, and this is how we invented the negative numbers. The negative numbers. Alright, so let's take a look at these negative numbers. We know that the motivation behind positive numbers are counting objects, and what is the motivation behind negative numbers? Well, it turns out that the motivation behind negative numbers is Arabic mathematicians who are trying to come up with new ways of representing numbers in finance. And it really makes sense when you think about it because, for example, a loan or a debt can be expressed as negative numbers, you lose money, while a salary can be expressed as a positive numbers where you gain money. And the intuition behind negative numbers is really straightforward. So let's consider how this intuition works out with the basic operations of addition and subtraction. In addition and subtraction, you know that from elementary school math that subtracting a positive number is equal to adding a negative number. 3 minus 1 is equal to 3 plus negative 1. And that's all fine and good, and what if we think about the other two operations, multiplication and division? Well, it is known and also defined that two minuses make a plus. For example, if we multiply negative 1 by itself, the negative signs cancel out and we get a positive 1. So this is probably why the square root of positive numbers, there are two square roots. One is negative, one is positive, and they have the same absolute value. However, you're always curious and you want to ask, what if we take the square root of negative numbers? What is the square root of negative 1, for example? And ever since elementary school through high school, your teacher has told us, no, you cannot do that. You cannot put a negative number under a square root. But is that true, though? After all, Mathcal is dedicated to not only telling stories, but also dismantling everything your teacher ever told you. So I'm just going to say that there are more things to that than you can do a square root, and there's going to be more on this later. Alright, with that cliffhanger, we can move on to some expanded number systems. We have the positive numbers and the negative numbers. For example, we see this lumbered line over here, and we know that we can go both ways with equidistant distances. And mathematicians, as you know, weren't always satisfied. What if we move on to somewhat different numbers? We look at what's between those 2 points on a number line. And this is where the rationals come in. So the motivation behind the rationals, as you may or may not know, is ancient Egyptian and Babylonian geometric masters and teachers trying to calculate the surface areas, volumes, and measures of different geometric shapes. One good example of how they come into use with calculating volume is this cone as an example. The cone, as from geometry it is known that its volume is 1 over 3 times its bottom surface area times its height. V equals 1 over 3 times sh squared. And let's look at this 1 over 3. This is unlike everything we have seen before. This is not a positive integer, this is not negative integer. Then what is it? So this is how the rationals were invented. We have fractions such as 1 over 3, 2 over 5, etc. And the definition comes naturally for rationals. It is p over q, this fractional, where p and q are integers. P and q are integers. And the set of rational numbers, that is, the collection of all rational numbers, including the integers and also these fractions, is written by this big Q over here, which stands for quotient. The first letter in quotient is Q. It's not necessary that you have to write this in this font called Blackboard Bold, but this is kind of a convention that math people usually use to make themselves look really fancy or something. So we have to look at the rationals, which kind of fill up our number line on the previous slide. This number line here, we have some more intuition on what goes between two integers, but are these all of them? And here is a story on the discovery of other number systems inside a number line. So we've all been familiar with the Pythagorean theorem. Inside a right triangle, a squared plus b squared equals c squared, where c is the opposing side of the right angle. And if we look at the most simple right triangle to construct y with side length 1, we can think of its hypotenuse as 1 squared plus 1 squared and take the square root of that. But what is this? What is the square root of 2? And this is where a guy named Hippasus comes in. This is a Pythagorean theorem, and the story that goes about Pythagoras is that he had led a math cult that worships positive integers and detests beans. So I don't know what Pythagoras has against beans, but he also has this dilemma against all numbers that cannot be expressed as fractions of integer numbers. So this guy named Hippasus, he had raised initially the question of the length of the hypotenuse of this right triangle over here. And slowly the members of Pythagoras' math cult realized that no, this is not an integer and this is also not rational. It cannot be expressed as a fraction of two integers. And just like everyone who find their cult values being challenged, Pythagoras' disciples got real mad, and this, as the story goes, threw Hippasus overboard on a trip in a lake, and he drowned to his death. So kids, this is why you don't join cults, and even if it's a really good paying math cult and you really love math, please don't join a cult. And this, aside from discovering the reals, Hippasus' death really showed that there is a long history of mathematicians dying for math. But more on that later. So it turns out that the root of 2, due to some really precise calculations, equals to this decimal over here, which has no repetitions as far as we can see. So it is not rational. So what is it? This number is clearly existing. We know that it falls on a number line somewhere between 1 and 2, approximately this point to be precise. It can be represented as a point of the number line, so we can say that this number, it exists. The root of 2 exists, so it is a real number. And this is the concept of the reals. And it is hard to define the reals, but we can think about all numbers that can be represented by a point on a number line. So we have this notation R for the reals. And in case you're wondering about this blackboard bold over here, there are some different representations of the letters we have. So conventionally, we use capital N for the natural numbers, the counting numbers, that is, integers that are greater than 0 or greater than or equal to 0. There's a debate here. And we have this Z used to represent integers, which is from a German terminology. We have seen Q and R to represent rationals and the reals. And there's this C here, this mysterious C. What does it represent? Well, more on that later. First, now that we know everything from the integers to the reals, we can see how cool we can play some tricks with these numbers. Interesting facts. So, in the last section, I have stated that the root of 2 is irrational. It cannot be expressed as a fraction of two integers. But why is that? Maybe some teachers told you to take it for granted, but math is all about proofs, and I'm going to prove to you why exactly the root of 2 is irrational. And here we're going to use proof by contradiction. Maybe you have heard of proof by contradiction before. A brief aside for anyone who hasn't, a brief aside on proof by contradiction. And the proof of the square root of 2 is irrational is how most students of math approach the proof by contradiction initially in class. So the proof by contradiction goes like this. Suppose we have statement A, and we want to prove that it is true. So how can we prove that the statement A is true? Well, we can say that if A is true, which obviously it is, then everything is right. Nothing is wrong, and everyone is happy, right? Yeah, so that is what we call a direct proof, but often it is kind of hard to check that this part, everything is right, because obviously you have to check everything, and that is quite work. So we use proof by contradiction. The proof contradiction states that if A is wrong, obviously we know that A is right, but just suppose, bear with me, that A is wrong, then if A is right, then something goes wrong. And we have found a problem. So A is not right. And the essence of proof by contradiction is by narrowing down the scope that you're going to check, because this part, something is wrong. You only need to check one thing that is wrong if A is right, but with direct proof, you have to check everything. So this is proof by contradiction, and we're about to see how this entire thing works in a second. By proving the root of 2, square root of 2 is irrational. So the classic contradiction statement goes, suppose the statement you're trying to prove is wrong. Suppose the root of 2 is rational. Then recall the definition of rationals, and the root of 2 can be expressed as a fraction of p over q, where p and q are integers. This is a definition of a rational that can be expressed as an integer fraction. So we can do this. And what if p and q are integers? Well, we have all been familiar with the notion of a reduced fraction. We can assume that p over q is one of a reduced fraction. Is a reduced fraction. Because if it isn't, we can always simplify p over q to a simplest form. So we assume that it is a reduced fraction. So this means that p and q have no common divisors. We cannot reduce this fraction p over q further than it already is. And this is going to become important. Let's see how it does. Now we can square both sides of this equation. We say 2 equals p squared over q squared, so p squared equals 2 times q squared. So this is a problem here. Let's see. P squared equals 2 times q squared, and q is an integer, so p is even, right? P squared is even, so p is guaranteed to be even. Since p is even, we can go and write p equals 2 times k, where k is also an integer, so for k squared, we substitute it into this equation. 4q squared equals 2q squared, and q squared equals 2k squared. So this means that q is also even. Q is also even. And can you see a contradiction in here? This two, we have stated here that p and q have no common divisor. So it is technically illegal for p and q to be both even, because then it will share a common divisor of 2, which leads to a contradiction. So if the root of 2 is rational, then something goes wrong. Therefore, the root of 2 is irrational. And we are done. This is your first introduction to proof by contradiction. This as well gives you some intuition on the structure of these irrational numbers, these irrational square roots. And as an exercise, you can try to prove that root of 3, root of 5, root of 7, etc. are irrational. It goes similarly to this proof. You can try it out yourself. It'll be a good exercise. So we have proven that the root of 2 is irrational. What else? What else can we do with these interesting number sets, integers, rationals, and reals? Well, one thing mathematicians tend to do when they look at a set of something is to determine its size. So we know we have n, the natural numbers, 0, 1, 2, 3, so on and so forth. These integers, q the rationals, and r the reals. We're going to use this notation here. We put n inside 2 vertical bars to denote the number of naturals. In general, when we put a set S between 2 square bars, this means the number of elements in S. So we can come and look at the size of all these number sets. The integers, rationals, reals, and also, I guess, the natural numbers. Obviously, they're all infinite. There's no finite number of any of these kind of numbers, but can we compare them? That is, are some of these sets bigger than the others? And when I say bigger, I mean they have more elements inside them. Well, I'm going to make a claim right here and say that the number of natural numbers is equal to the number of integers and also equal to the number of rationals, which is smaller than the number of reals. Well, I anticipate what you're going to say. You're going to say, but that's absurd. How can these number sets have the same number of elements when obviously n is contained in z, z is contained in q. They have a containment and there are other elements other than those contained set, and so that cannot be real. Unfortunately, I'm going to tell you that your intuition is entirely wrong. Oftentimes we try to approach a problem with intuition before logic, and this does not work well with any problem that concerns infinity. So you have infinity right here, and you try to tackle this problem with your intuition, and guess what? That's not of use. Your intuition is not entirely wrong here, but rather just used in the wrong sense. So I'm going to show you how can we prove rigorously that the number of naturals is equal to the number of integers. So if I tell you that there is a 1-to-1 correspondence between the elements of naturals and the elements of the integers, would you say that, taking this for granted, they have the same number of elements? Well, I guess. So if you have a set 1, 2, 3, and a set 4, 5, 6, we can establish a correspondence that gets 1 to 4, 2 to 5, and 3 to 6. And this proves that the set are all the same size. We can apply the same argument here with infinite sets. So we line up the naturals as we expect them, 0, 1, 2, 3, 4. And how do we line up the integers? We establish a 1-to-1 correspondence. So we also start with 0, but after 1, we put -1. And 2, then -2, and so on and so forth. And is there a problem here? We know that those two sets are both infinite. This list goes on forever, and this correspondence is well defined. Given a number in the naturals, we can always find a number that corresponds to it in the integers, so there is no problem. You may take some time to wrap your brain around this concept, this new intuition of mathematics, but after that, you can fairly confidently that yes, the number of naturals is equal to the number of integers. So that's one problem solved, let's move on. We still have to prove that the number of integers is equal to the number of rationals, and that is just as easy as I may say. Similarly, we try to establish a one-to-one correspondence between z and q. We line up z, as we have already done, 0, 1, minus 1, 2, minus 2. I'm going to write some more terms just for clarity, for -4, so on and so forth. And how do we line up q? Remember, since these sets are both infinite, we only need to come up with a way that lines them up in some clear order to ensure the correspondence is well defined. That is, if we find an element in Z, we can always directly find an element in Q that corresponds to that element in Z. So think of it this way. We have 0, then 1 over 2, negative 1 over 2. And what's next? We put 1 over 3, negative 1 over 3, 1 over 4, wait, that's wrong. Never mind. 2 over 3, negative 2 over 3, and 1 over 4, negative 1 over 4, so on and so forth. So maybe you see what we're trying to do here. We line up all the rationals that share the same base denominator. So we have 2 here, we have 3 here, and 4 here, and the list goes on. So this is a well-defined established correspondence between the elements of the integers and the rationals. So ask again if there's a problem. Do you see one? So there is no problem. And in fact, the number of integers is equal to the number of rationals. So we can conclude that the number of rationals, integers, and natural numbers are all equal. This doesn't mean factorial, by the way. And what about the reals, you may ask? We have left out the reals so far out of the discussion, so what about the reals? This size of the reals argument really involves some extremely hard concepts to digest, so I'm going to claim that it is known. And please don't use the word it is known when writing your proofs, that the size of R, the number of reals, is greater than the size of Q, the number of rationals. So we have a comparison, but mathematicians are never satisfied. They ask, so they're both infinity. Some infinities are bigger than other infinities. So is there anything in between? Because when you get to read further on this subject, you know that the size of R and the size of Q are both important infinities in the concept of mathematics, and mathematicians are trying to extrapolate from those two and find other infinities that they can establish a size argument. Well, there is this theorem to answer this burning question. The theorem states that it cannot be proved that there is another infinity between R and Q, but it can also not be proved that there aren't any more infinities between R and Q. So basically the theorem statement is that we can never know. So this is kind of an example of how simple number systems like N, Q, and R extrapolate pretty quickly to higher level mathematical questions that have baffled mathematicians up to this day. This is a common experience for anyone who tries to dabble in math, and if this is your first, enjoy the process. And before we move on, one last interesting fact that we can do with NZRQ is the cool stuff you can do with the root. My favorite root. In fact, this is the root of 2, Hippasus died for it, so let's do this root full justice and see what we can do, all the fun things we can do with the integers, the rationals, and 2, the root of 2. So we form some real numbers from the root of 2 and the rationals. For example, we have this 1 plus root of 2, 3 plus 2 root of 2, 5 plus 3 root of 2, so on and so forth. And we can generalize them in the form of a plus b root of 2, where a and b are both rationals. So the form of 2 over 3 plus 5 over 3 times root of 2 is also legit. And let's apply the 4 basic operations to them. First of all, addition and subtraction. So we have a plus b root of 2 plus or minus c plus d root of 2. And we just group the like terms together as we have learned to do in basic algebra. This is equal to a plus or minus c plus b plus or minus d times the root of 2. You can see that, right? And this turns out to be the same form because the rationals a, b, c, d are closed. That is, if we apply the 4 operations to them, they are still rationals. So they still satisfy the form a plus b root of 2 where a, b are rationals. So we can say that this result is of the same form. The same goes for multiplication. In multiplication, we multiply these two elements of r instead of adding them, and we expand this term by term. AC plus 2BD plus AD plus root of 2. So that is our answer. And we can group the like terms together, so these are rational. The first term is rational, and the coefficient of root of 2 AD plus BC is also rational. So we can deduce that this multiply result is still of the same form as a plus b root of 2. Cool, isn't it? But those two seem kind of obvious, addition, subtraction, and multiplication, so let's look at what it happens with division. So we have a plus b root of 2 divided by c plus d root of 2. And we use this algebraic method of rationalizing the denominator, as you may have heard. And we also use this handy little algebraic trick right here. We multiply the denominator and numerator by c minus d root of 2, a plus b root of 2 times c minus d root of 2, so we can rationalize the d root of 2 term here. And this turns out to be that. This big fraction over here with a denominator of c squared minus 2d squared. And if we separate the terms, we can see that the final answer, ac minus 2bd over the denominator plus bc minus ad over the denominator times root of 2. Those are still apparently rational. They all belong to Q. So we can conclude that the division is still of the same form. So if we take a real of the form a plus b root of 2 where a, b are rationals, this sign means belong to, then whatever operation we apply it is still the form of a plus b root of 2 where a and b are rational. This is kind of cool, but what application does it have? What does this mean? Well, this is a little trick for you to think about in our later videos. And I'm not going to spoil any of the surprise here, so that's that. And finally, we're going to address, before we end this video, one last form. At the beginning of this video, I had stated that the root of -1 does not exist, as per your teacher. But is she right? Or is she gatekeeping some more interesting, juicy mathematical things from you? Let's check this out. So, a habit of mathematicians when approaching something they don't understand or don't have yet is to downright invent stuff. So, we can say that this exists. We can invent something to represent the square root of -1. Let's call it an imaginary number because it's entirely up in our heads. We represent it using I, the first letter of imaginary. And what's the motivation behind this one? Well, apart from mathematicians' rampant curiosity, the motivation is for solving polynomials. And a polynomial is an equation of this form. You may have seen this in more advanced math classes. This integer powers of x plus, yes, this is a polynomial, and they're trying to find the roots. That is all the values of x that makes this polynomial stand. This equality holds. So this is solving a polynomial requires sometimes use of roots of negative numbers because there is this theorem that states that an polynomial of degree n has exactly n roots. And if the root of -1 doesn't exist, then this theorem is not satisfied and something goes wrong. So mathematicians have invented this notation for negative root I, the imaginary number, or rather I squared equals -1, because there's something that goes wrong with this equation. I'm not going to say what. If you're interested, you can try to prove that something is wrong with this equation. And this has formed the complex number set C, the complex numbers. That is all numbers up to form a plus bi. And this is the real part, the imaginary part, where a, b are all real numbers. This is done by the mathematical goat Euler, as you have known and probably worshipped if you're a math nerd like me. And there are a lot of fun stuff we can do with the complex numbers. More on this later, because frankly, I have talked a lot about numbers too much gap today, and you need some time to process all this information perhaps. So that is the first episode of Mathical Math with Stories. I hope you enjoyed this episode of Rampant Stories, and also random facts about numbers that just foreshadow and do nothing at all. Anyway, thank you for watching. Please like and subscribe, and stay tuned for our next episode, which I promise is going to be less yap heavy.